Test. 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 2, 3, 4 seconds. Okay, the slide is already uploaded to NTU Learn. You can, if you need it, you can go and download it. Okay, so this week I will cover the breadth-first search, and today I think today I will cover the depth-first search, and I think maybe okay today I will cover, let's see, depth-first search. I'll cover the depth-first search, maybe 4-5 slides only. Then after that I will cover another things called backtracking and dynamic programming. Dynamic programming, I think the notes doesn't have too much details, but actually you are using, just you didn't know that that is the dynamic programming. Since quite a lot of people are asking, then just let you know what is dynamic programming briefly. Yeah. So, and then we will use two very well-known computer science problem, which is one is Adqueen problem, and the other one is knapsack problem. For these two, I would say it's kind of like a strategy or implementation technique lah. Yeah, not implementation technique. I think it should be kind of a strategy. Yeah, kind of a algorithm strategy. Yeah, to solving certain problem. Yeah, not all kind of problem can be used, but quite a lot of problem can, real world problem you encounter actually can solve by backtracking and dynamic programming. So I think I will not be able to cover everything today. So probably today we'll cover that first search to backtracking. Maybe Wednesday will cover the dynamic programming, and the other one is the matching problem. Yeah, which will cover on I think Wednesday, and next week. Yeah, maybe we will be able to finish the lecture next Monday. And next Wednesday will be kind of like an overview, revision, or any clarify your doubt. Yeah. Okay. Good. Slowly 35 viewer. Yeah, I think I already released the assignment 7 and 8, so-called, it's just combined two. So to let you have more times, this one will be all the way till week 13, Saturday. Yeah. Then this is the last one. So should be, I hope it's hard enough for you to do over 3 weeks. I would say the question definitely not something I don't want to like something like few minutes you can finish it, then that called assignment. So it should be can be something. I hope it can be done like let you think over the few weeks time to really understand what this searching is about, what is exactly the graph is about. Maybe I would say this one still in the introduction level. Graph is theory is a very big topic, yeah. But at least think we cover breadth first search, depth first search, all this backtracking, yeah, and then this coming Wednesday the dynamic programming, and then also the matching problem. All this you really know what it is. Not just I tell you A, then you know A. Yeah, actually you don't know really what is A, but anyway, lecture notes say A is A, then it's just A, So yeah, it should be take hours. Yes, it should be take hours. That is what I hope it can be. Yeah. Yeah, but you don't have to worry so much about the lab test. Of course, lab test is 2 hours, including the MCQ. So yeah, the question cannot be that difficult. Otherwise, become pointless. Everyone don't know how to do. Then what's for having the test? Yeah. So yeah, the test question will be, if you can handle the assignment, you do it by your own. Your implementation skill are already strong enough. It should not be a too big issue. Yeah, it should not be a too big issue for your lab test. But if you are those people are just like copy and paste your friend's work, yeah, then maybe get caught, maybe didn't get caught. Then yeah, anyway, during the lab test you will know. Yeah, we got way to find out. Yeah, our question will tell you that, yeah, what is the consequence you copying people work. Yeah, okay. So today, last Wednesday, we already covered the breadth search. Breadth search basically is a level order. The level order, level order. So level order means that, yeah, you travel level by level, start from 11 in this example, then you visit the next level, 1 or 2. You can start, you can visit 1. If the question didn't set, that means you either 1 or 2 visit first, it doesn't matter. But normally we want to have the same output. Maybe we will tell you that in ascending or descending order, because the result will be very different. Then the next one will be this one. Then after that, the next level will be this one. Yeah, that's the level order. That's a breadth search. So when you see that you are trying to visit level by level, actually you are trying to do some kind of a queuing. So not surprising, if you look at the algorithm itself, you need to create a queue for you to sort out the visit order. Yeah, when you run this loop, if you observe carefully the process, actually in the earlier slide, you can see that actually you are trying to queue the next visit nodes, yeah, in the queue. So when you're trying to dequeue, the nodes is the next visit nodes, and then you are trying to adding all the is neighbor, which is unvisited. The purpose is like trying to let them queue lah, in short. Yeah, yes. I don't call it exam, it's a lab test. The lab test 2 is 20%, and the MCQ is another 20%. So the time complexity of the breadth search is depend on how you implement it. So because you can see that you run the loop, I think you are the worst is you visit all the edges. The worst case, you visit all the edges, and then all the vertex you will queue and dequeue once, because once they are visited, you will enqueue it. and then next time you will just dequeue it. So you won't re-queuing the, you will not queue the same nodes again. So they only queue once. So overall, is the vertex, no problem. The thing is the edge. If you write in the adjacency list, that means the edge, you can easily through the adjacency list to find out who is the neighbor. Yeah, so if I visit these nodes, I want to know all its adjacent C nodes, then you can easily retrieve it from the linked list. But if you are using adjacency matrix, you want to find the nodes. It's a 2D matrix. Yeah, so you want to find the adjacency list. You need to scan through every element, whether it's 0 or 1, whether it's 0 or 1, whether it's 0 or 1. So not surprising, along here, you will take V. So every vertex you will visit once and only once. So it's another V. So not surprising that the complexity will become the vertex square, the number of vertex square. And if you use the adjacency list, then it's the vertex plus the edge, the number of vertex plus the number of edge. And very likely depend. Yeah, I think depend. But in the worst case scenario, that means if your vertex is a complete graph, if your graph is a complete graph, yeah, something like this, complete graph. If you have complete graph, then the E will be the V minus 1 over 2, which have been mentioned earlier. So this one again is in V square. So in the worst case, whether you implement, if your given graph is a complete graph, actually you implement in adjacency list or adjacency matrix, no different. Okay, so that is the breakfast search we have talked about. We discussed on last Wednesday. Okay, yeah. The lab test is 2 hours. So yeah, now you should understand why the assignment always come with some MCQ question here and there, because 2 hours including the MCQ together. So you need to adapt that. I think the challenge is it's two different kind of a mindset. When you write the programming, is one kind of a mindset. When you do the MCQ question, is another kind of mindset to answer the question. That is probably the challenge in the final test. So you need to think what kind of, actually you should think about it is like what kind of strategy you should do is like during the lab test. Should you do the MCQ first, or should you do the programming question first? So that need to do some plan. I will release the schedule details. Hopefully this week after I arrange with the lab officer. Yes, all together. We unfortunately we won't be able to find another time slot to do this thing separately. So we have to do all two of them together. That's means the format is a bit very similar to what you are doing your current assignments. And then, but of course the times will be not 100 hours. It will be in 2 hours. Yes. No. 20%. We have mentioned actually it's considered a lab test 2 and the final quiz. Lab test 2 is 20%. Final quiz is another 20%. This assignment 5, assignment 6, assignment 7 and 8, these 3 assignment is contribute another 20%. So total, Of course, the final quiz including the first part. The final quiz including the first part. That's mean the concept, whatever you need to know in the first part will test you during the final quiz. Final quiz is 100% purely MCQ. Yeah. So sometimes you ask me whether need to know how to derive all this and that. And yes and no. Yeah, sometimes because it's an MCQ question, you may not need to really derive it in the very proper way. You also can find out the answer. Sometimes you need, but I think you don't have to write now the answer properly because it's just an MCQ. You write now properly, it's just for your own use only. Yeah, in the end, we only base on your answer to decide your marks. Okay, so okay, next one is so that is a breadth-first search. Next level is another approach is using the depth-first search. Depth-first search is something similar to your pre-order traversal in the binary tree. So the idea is I'm trying to travel as far as possible, as deeply as possible. And then after once I reach the end, once I reach a point which there's no more unvisited nodes, then I start backtracking. Yeah, I'm backing up. So it's like from 11, start again, same thing. I start from 11, and I travel to here. Then I travel to here. Okay, no more. Because no more neighbor which is unvisited. Then I start backtracking to here. Then next one, I will visit this one. Then I still got 2 unvisited nodes. Maybe I visit this guy. This guy no more. Then we'll visit back. We'll backtracking. We'll back to 3. Then carry on to here. Then carry on to here. And then no more. So I start go back. I start trying to return back to the previous node. Yeah, because all this, when I return, I check around, no more. I check around, no more. I go back, check around, no more. Then this one still have one more. Yeah. So they won't. Yeah, after that, this one all return back. Then visit this guy. Then the next one will be, I guess I put this one. Yeah. Then this one no more. Then next one will be this one. I think next one will be this one. After that, I will return. Still got one more 10 haven't visit. Try to visit the 10. Then no more. Then start backtracking. Then start backtracking. Okay, you're back to 11. That means you already visit all the nodes. So that is the idea behind of the depth-first search. So depth-first search, you can think is like, so you can trying to visit, whenever you find a unvisited nodes, you will trying to visit it first. The rest, you will trying to store in some memory, some place, so that later when you visit to the end of this, but along this particular path, you find that, yeah, you just now, you will think about it. This thing, yeah, I trying to visit as far as I can. When I reach certain point, no more. Then I will return back to the previous one. Then start visit another path as far as I can. Then, I think I visit this one first. Yeah, visit this one. Then no more. Then I visit the other one. I keep trying to search the path. Yeah, then after that is this one. Then after that is this one. And then this one. So, more precisely, no, I should be back to 2. Then visit this one. Yeah. So that is so you can see, I don't know whether you can observe that. Will it travel from 11 to 2? 11 to 2. You also can. Because when I visit, yeah, there's again same thing. There's the order is depend how your implementation. Because when I visit 11, should I go to 1 or 2 first? Is depend how you implement. If you implement, this means this one there's no if I have to set that it's in ascending order or descending order. That means I discover that 1 and 2 is an unvisited adjacent nooks to the 11 nooks 11. Then I need to decide, should I visit 1 first or 2 first? Yeah. So I mean, after I go back to 11, after you visit, no, because 2 is already visited. Just like other nodes, all the nodes you're trying to visit once only. Breadth search, depth search, you only visit the nodes once. So you won't go back, you won't trying to visit the 2. Yeah. Otherwise, you will fall into a loop. Forever, your program cannot stop. So you expect that you need to do something similar to the previous one. You need some marker to indicate that this nodes is already visited or unvisited. Secondly, you definitely need something. You can observe that the memory, the data structure you need is a stack. Because every time I visit, I know that, like when I visit 1, if you observe when I visit 1, green color, when I visit 1, actually there are 4, 2, 3, 4. 2, 3, 4 are unvisited, but I choose to visit 4. That means I need to remember 2 and 3 is still in my in I need in my list that later I need to visit them. But my strategy is, right, whenever I see a new things, a new nodes, I will try to visit it first. Yeah, until I cannot find any new nodes, I start going back to the a little bit earlier nodes, then to find any available unvisited nodes. So this is kind of a stack. Yeah, idea. You first last in, first out. The last unvisited nodes you will visit first. Last in, first out. Yeah. So you expect that you need a stack to build this. So yeah, it's monitor the next. Yeah, so you can see this is the directed graph example. So when you visit A, you realize that A got 2 neighbors, B and C. So we're trying to visit them in alphabetical order. And B, no, not only B, BCF is the neighbor of A. So we choose B. After I visit B, I find out that C is also the B neighbor. And then C is unvisited yet. So I will push it into the list. So it's something like, I will push, what I will do, I will try to visit, when I see the B, what is it? Do I have? Should I have okay. So you can see I need to create a stack. Then I will push the first nodes into the stack and mark it as visit. And then I start tracking. As long as not surprising, you definitely will insert the first nodes, push the first nodes. So the S definitely at the beginning not empty. Then you were trying to pick the stack and denote as W. Then to find, after that you were trying to find no unvisited nodes, then you port this thing back. Then you will push an unvisited vertex U adjacent to W. So you will push 1. So every time, every iteration, you port the 1 or you push 1 nodes. Push an unvisited and mark it as visited. So if you're trying to do that idea, that means when I visit B, I will push it. When I visit A, I know that there's a B is a neighbor. I will push it into the stack. Then mark it as visited. Mark it as visited. Put the the box. Then after that, I'm trying to go to here. So in my stack, there's a B. Yeah. Then I find that B also have a neighbor C. So I will push C into it. Then mark it visited. Yeah. Then after that, you'll find that C, yeah, now is a B and C in the stack. Yeah, but C has no more. You can see that C do not have any. Yeah, this guy does not have any neighbor. So adjacent to it. Yeah, you can see it's a directed graph. Yeah, directed graph. So no neighbor. So too bad. You have to port this thing out. Then you are trying to see B. B, does it have any unvisited nodes? Which is D. D is unvisited. So you will add the D into it. So you will push D into it. So do you have to port B first before push? No. So B, because B still have we port the C out because C has no more unvisited neighbor. So we will port it out. So B still have. Okay, sorry, I think I missed out A. Yeah, A also in the list. I never port it out. So, sorry. Forgot. A is the first node. A is the first one I push it in. A is the first one I push it in. Yeah. So as long as you have the unvisited, as long as I still have some unvisited neighbor, I will push into the stack and keep it. So to remember, this guy still got path can going through this particular nodes. So yeah. So C is no longer able to move further. So I will port it out. Then I will try to D. D also the same scenario. You can see that D has two neighbors, A and C, but both are visited already. So after you push it in, the next moment you have to port it out. Yeah. Then after that, you are trying to B again. You go back to try B. You pick the B, but B also have no more neighbor. You have to port it out. Yeah. Then next one is A. A still have one more. So A can try to visit F. Yeah. So A, then you push the F. But F, after you push it in, you check again. And F also have no more. So in the end, yeah, you visit all the nodes. But these two again, you can't visit it because you have there's no path from A to H and A to E. Because these graphs are not strongly connected. So this means after I scan through, I find that there are two unvisited nodes. Yeah. There's any, not only two, there's any unvisited nodes. That means this graph is not strongly connected. Yeah, but I think you need to try out all. Even you find, like if I start from, because the thing is depend the start nodes. Yeah. This thing conclusion, you want to conclude that whether the graph is strongly connected or not strongly connected. Okay, if you need to find, as long as I can find one example, one starting nodes, not giving me, not let me visit after I apply the depth first search. In the end, there are some nodes. Any nodes is unvisited, implied that this directed graph is not strongly connected. But you want to show that this particular directed graph is strongly connected. That means you need to is strongly connected. That means you need to try all the nodes at the start nodes. That means I try A cannot. Then I try B. A can. Let's say A can. For example, A can visit every nodes B, C, D, F. Then I need to try B. After I try B, apply the depth first search. I need to try C. After apply the depth first search, it is also visit all the nodes, able to visit all the nodes. Then I try D, F, all of them. Then after I go through all of them, then I confirm that based on the definition, strongly connected is like, yeah, any vertex can find a path to any vertex. Yeah. So that is the how you find the strongly connected, the graph, whether the directed graph whether is strongly connected or not. Yeah. How do we keep track of the visited nodes since you put? Yeah, that's why you need another, maybe an array to indicate that whether they are visited or not visited. Yeah, so you probably need to, yeah, here there's a mark the V as a visited. Yeah, whether it's visited or unvisited. Of course, or you can, that's in your graph, structure, a few way lah. I think in the graph structure, I need to introduce another member, another field, yeah, called visited or not. Yeah, something like that. It just need to have a boolean or integer, just indicate 0 or 1. Yeah. Does it matter we use strongly connection? I think no. Both, as long, because both are trying to find the path. So breadth first search is trying to level by level. In the end, you also can find out. Yeah, but the key is you want to know whether it's strongly connected or not. You need to try all the vertex. You need to check through all the vertex. Whenever one of them cannot find a path to another vertex, yeah, then you can end already. You can stop already. Definitely, this is not a strongly connected graph, directed graph. So every time you travel a nodes, you need to look through the array to check. You don't have to. Why you need to look through? Because you know whether these nodes, whether is adjacent to it or not. So you don't have to check every nodes. For example, if I have vertex 1, vertex 2, vertex 3, vertex 4, vertex 1, vertex 2, vertex 3, vertex 4. Yeah, maybe they are connected in this way. A simple one. A very simple graph. Yeah, so when you visit 3, you don't have to go and check whether 1 is visited or not, right? When you are visit 3, give another color. Yeah, when you are visit 3, you just need to check its neighbor 4 and 2 and 4 whether it's visited or not. You don't need to bother about vertex 1. So you don't have to check through all of them. So strongly connected means that from any vertex. Yes, the definition is in the very first graph lecture we have mentioned about it. Means that the last nodes must be able to get back. No. Strongly connected doesn't means the last nodes must be able. It's after you go through this that first search, you not surprising that in the end, yeah, this function can stop because your stack is already empty. Your stack already empty. That means you basically already go back to the initial nodes. Then at that times, you just simply check the array, yeah, whether you already visit all the vertex or not. If you can't visit all the vertex, yeah, not surprising. That means this is not a strongly connected nodes, but strongly connected graph. 1, 2, 3, 4, 1. Yeah, if it's a 1, 2, 3, 4, 1, okay. So you visit 1, okay. I push 1 into the stack, in the stack. So let's say I visit in the okay, I better use same color first. Okay, then I green color. Okay, let's say all the green color is unvisited nodes. Different. Never mind. So I visit in the ascending order. So I visit 2. So I visit 2. So after I visit 2, I will push 2 into the stack. Then I'm trying to visit 3 because there's a unvisited node 3 is unvisited. Then I start visit 3. When I visit 4, after I visit 3, I will visit 4. When I visit 4, when I visit 4, no visit vertex are adjacent, no unvisited. There's no unvisited nodes already. So I go back. When you start port, actually this is the backtracking. This part is the backtracking. You start backtracking already. Then 3 also no more. You start backtracking already. So 2 also don't have. You backtracking already. In the end 1 also no more already. Okay, you also pop out. So is it strongly connected or not connected? At this moment, actually, you still don't know. You have to start from 2 again and try it out. You need to try 3 again. You check it out. Then you're trying to start from 4 again. Then you're trying to check whether you got you are able to visit all the vertex. So does not have to be No, the given graph can have a cycle because it is a graph. But the thing is like the path, you find that, so this one you will form, after that, of course, this one very simple in the end. You will form this one, 1, 2, 3, 4. This is the depth first search spanning tree. That is the depth first search tree or spanning tree. So if a vertex have several neighbor, it will be equally, so in any order. So you need to take notes the implementation. You may get very different result from your friends because you implement in different order. So if the graph is strongly connected, then the tree construct, you can construct a spanning tree. That's tree called depth first search spanning tree. I think I should call more precisely. Maybe should name it depth first search spanning tree. Then earlier one is the breadth first search spanning tree. So there's the tree. Based on just now you visit the earlier one, this is the spanning tree. Okay. There's no cycle in the tree structure. There's no more cycle. So we only work on directed graph most of the times. Not really. Depend on the problem. The problem may be there's no directed graph, then there's no directed graph. It can be directed, can be undirected. But both breadth first search, depth first search can be applied. No problem. Because certain graph algorithm maybe only can apply in the directed graph or undirected graph. So, but if it is weighted, then we have to take notes. You find that breadth first search and depth first search will not consider weight. Do you notice that? No, I never mentioned the weight because how you decide the weight when you coming in using the breadth first search is just visit the nodes, trying to visit all the nodes once. They are trying to, these two algorithm is trying to think a strategy. How can you give me a graph? How can I ensure that I have a method systematically visit every node once? So when you have the weight on the edge, I basically can't do anything in these two algorithms. I still based on my strategy to visit. Of course, maybe you can introduce some weight. Same thing. Unless you give me the weight, is for me to decide which one I should visit first. The one with a heavier weight or lighter weight. That means you need to modify a bit your algorithm. The graph cannot contain. The graph can contain, but the tree cannot. You can see this spanning tree, there's no cycle. I think it is a spanning, since it is. No. They just trying to tell you that after you applying the depth first search, the visit path, just now you recall, I first visit B, then I visit C, and after that I visit D, then in the end I visit F. This is a spanning tree. Yeah, spanning tree cannot have cycle. Yes, but the graph itself, the original graph itself, no problem. You want to have a cycle, then here there's a one cycle. Yeah, here itself is another one. Then this one, yeah, this one also. No, this one not cycle. How to get a cycle? No more already. I think only these two. Yeah. Okay. Yeah. So the breadth-first search using BFS, using the BFS breadth-first search, use the queue. Depth-first search, use the stack. Because breadth-first search is trying to sort out the visiting order level by level. Whenever you see there's an unvisited nodes, you are trying to visit it as soon as possible. But depth-first search, the strategy is like whenever I find a new nodes, unvisited nodes, I will try to quickly go and visit it. Those nodes earlier I discover still in the data structure, I will keep it at the bottom. I will visit them later. So this is like a kind of a last in, first out. The latest one you will visit first. The oldest one you will visit later. Yeah, so you were trying to use a stack to stack them. Yeah, to remember that still got some old nodes you haven't visit. Then every time you trying to discover the unvisited nodes, you will select the latest one, the new unvisited nodes first. So that will let you try to travel the things as far as you can. Yeah, before you come back, before you backtracking, you are trying to recover back to the earlier stage, then to find any unvisited nodes. Yeah, which you have discovered earlier, but you have not visited them yet. Yeah, you are trying to visit them later. So not surprising, that first search they are using stack. Okay. So a lot of application, like just now the strongly connected component is one. Yeah. Then finding the connected, whether they are connected component or finding the card. Yeah, you can see that I can find in the earlier example E and F. Yeah, I can find out these two are separate, can be separated. Yeah, or solving the puzzle, shorter path. Yeah, you can use the finding, not shorter path. You can finding a path. Yeah, you finding a path. It may not be shorter. Yeah, but finding a path, you can use the depth-first search. Yeah. So another one, topological sorting, is just like some typical example is your module. Yeah, the course you need to take 1103. Yeah, then you need to take after that the next level is 1107. Then after taking 1107, you need to take the forgot 1810, is it 1812? Yeah, 1812 discrete mathematics. Yeah, after you taking these two, you can take your 2101. After you taking 2101, no, then this one can let you take OODP. OODP is 2002. I think now they change back to 2002. Then this one, after you taking this, you can take the database. Database is what? 2007, is it? Okay, yes, 2007. 2007. Yeah, then you can take 2007 and so on and so forth. Yeah. So this is a kind of a topological sorting. Yeah, based on the prerequisite, you can come out the it can come out this kind structure. So sometimes it's like they give you is the the table, the data, then give you all the prerequisite. Yeah, I think here only have the prerequisite. Yeah, some places maybe have the other criteria. So you can use all this to build out a graph, and then that kind of a graph is a topological sorting. You can through this kind depth first search to find out, to build out the this kind topological structure. Yeah. So that is one of the example. Puzzle wise, that's when you have a map. Yeah. So I think typically, I should find it. I should attach an example. Maybe you some obstacle you cannot go, some obstacle you cannot go. You have some obstacle cannot go. You have some obstacle cannot go. Yeah, you need to find the path from here to here. Yeah. So you're trying to you're trying to move as far again. You are using depth first search to move as far as you can, as far as you can, as far as you can. Yeah, whenever you depend what kind of strategy, I can try to always move to the right, move to the right, move to the right. When I try to no more move to the right, I try to return back. Then I try to move upward as far as I can, as far as I can. I encounter this obstacle, that's when I will return back. Then I will try to visit the next one. Cannot right, cannot up, or I trying to left. Yeah, after left, I always trying to visit. No, this one should be the other. No, here this step wrong already. If the strategy is like I trying to, my visit order is move to the right, then move up, then move this, then after that move down. Then you expect I will use another color. I will trying to move from here all the way. That's mean you can imagine this is a graph. You trying to move until here, no more. You try you backtracking. Then you try another path. Then no more. Then you try another path. Is one step here. Then I still can move up. Then I try here. Then I found it. Yeah. Of course, sometimes the puzzle can let you backtracking quite a while. Certain path is totally not correct. Yeah, you reach the things, cannot left, cannot right, cannot up. You will start backtracking, and then you try another new path. So that is actually using the depth first search algorithm. Yeah, for again the assignment 7, yes, there's a I think I found I upload the one of the test case wrongly, so I already collect it yesterday. So you not surprising today you try it work again. Yeah, I already correct it, so should be okay now. Yeah, so that is the depth first search. Same thing, you find that depth first search. Yeah, each node also visit once only. That's the purpose we want. Then the edge is travel forward once and then backtracking once. Yeah. So using the adjacency list, same thing. Your complexity will be the number of vertex plus the edge. Yeah. Okay. Then adjacency metric, will be same thing lor. Yeah. Why I forgot to put. Yeah. That is for adjacency metric. In these two examples, you find that adjacency list will be better, but sometimes adjacency metric will be better. Yeah. Depend your algorithm. So here we only use the breadth first search and depth first search algorithm. But basically you can do a lot of things already. Then in the next stage, in the 2101, they will cover the Dijkstraat algorithm and the prime algorithm in the next level. And there are a lot more. Yeah, I would say that there are a lot. Depend the weight one, the weighted graph. Yeah, you can see breadth-first search and depth-first search cannot use. And then when you're talking about the weighted graph, then you find that weighted graph also need to consider the weight can be negative number. Then that is another algorithm. Yeah, so then directed weighted graph or undirected weighted graph, yeah, they got different kind of algorithm. Find the shorter path or find the minimum spanning tree. Yeah, they can have a lot of different problem. Yeah, you need different algorithm. Okay. So that is the breadth-first search and depth-first search. I think I still have some times. So next, this week, yeah, I will cover another thing. Yeah, the backtracking and this is the additional one. The dynamic programming. I think I probably don't have time to cover too much. I don't have time to write the notes. So here, just take notes that I just give you. Actually, all these things you find that there are a lot of things you actually using dynamic programming. Just you don't know that they are dynamic programming. Yeah. So I just let you know what it is. For the, I think you're talking about A-star search. A-star search, I think, if I'm not wrong, it should be covered in the module 3005. AI, because all this is trying to search the path. Then AI, the robot need to find the path to, yeah. So not surprising they will cover it in that level. In 3000, yeah, in 3000 is a 3000 module, artificial intelligence. Yeah. So that's why I will not cover it. Yeah. So one of the typical example, yeah, depth-first search actually one of the key is using this kind of backtracking strategy. Yeah, strategy. So one of the very classic example is the Adqueen problem. In fact, is someone come out this problem in 1848. Yeah, more than 150 years ago, more than 150 years ago problem. Yeah. Then what is an Adqueen problem? Basically, Adqueen problem is like you have a 8 by 8 chessboard. Yeah, and then you're trying to put the queen. Yeah, you're trying to put. Of course, you only can put 8 queen in the board because the queen can move, yeah, horizontally and vertically and diagonally. So you're trying to put 8 queen on the board, yeah, such that no queen can attack each other. Yeah, that's the things you need to do. But how to put this 8 queen on the board? Yeah, one very silly way is like trial. Yeah, that's mean every position you either put a queen or not put a queen. You either put a queen or not put a queen. Either you put a queen or not put a queen, and so on and so forth. So doing that, yeah, is 64 choose 8 position. You have a 64 position. Yeah, you're trying to choose 8 position. Yeah, 4.43 billion way. Yeah, so not very practical. Okay, some people are a little bit smart. They think, okay, if I put a queen in the first row, yeah, in the first column or in the first row, yeah, definitely this particular queen cannot put in the same row or same column. Okay, then you can reduce. Yeah, so each row can contain exactly 1 queen. So you can put it here, you can put it here. That means each row you can put, so you can, among these 8, you can choose 1 position. Then here only left 7 position you can choose. Then here you can choose, so every time you got 8 possible times. That means here got 8 possible position. After this one, select 1 position here. Then the second, okay, I set row, then I should choose the other way. Okay, if I choose this one in the first position, so this one got 8 possible. I can choose here, I can choose here, I can choose here, I can choose here. So since I choose here, the next one only can can have 7. I only can choose among these 7 position, one of them. So there are 7 possible. Then the next one only left 6 possible position. Then 5, 4, 3, 2, 1. Yeah. So total add factorial. Okay, not bad. You already improved from 4.43 billion to 40,000. Yeah, 40,000. But is it smart enough? Not really. Yeah. Actually, you can use the backtracking. Yeah, you find that this one still quite a lot. 8 by 8, yeah, what happened is 10 by 10. Then become 10 factorial. Yeah, n factorial, you should know that it's quite scary. Yeah. So therefore, people come out this backtracking algorithm to solve this problem. Well, we still start by placing a queen at the top left corner of the chessboard. Then you trying to place a queen in the second column and move her until a place where she cannot be hit by the queen in front, in the first column. Then that means if I have a chessboard, okay, make my life easier. I don't draw so many. I trying to have a 4 by 4. Same problem. 1, 2, 3, 4. 1, 2, 3, 4. Okay. So if I put a queen here, then I will trying to place a queen in the second column. Yeah, and move her until a place. So I trying to put here, cannot. I put here, cannot. I can put here. Until where she cannot be hit by the queen in the first column. Yeah, it cannot hit by the first column. The first one can hit this one and this one and this one. So the first 2 position I cannot choose. I only can choose the third position. Yes, you can think so. So then I place a queen in the third column. Yeah, I start trying to place a queen in the third column. Okay. Then but the problem is come out. This one cannot. This one also cannot. This one also cannot. This one also cannot. All of them cannot. Yeah. So then I need, if there's no place for the I queen, that means the third queen at this moment, then the program need to backtrack to the earlier one and then find a new position. So I have to backtrack. That means I have to remove this one. Then I need to add a new one, a new position. Yeah. Then the I one have to carry on to search. This is the next possible position. After I put this one, I carry on. This one cannot. This one, also cannot. All cannot. This one can. Yeah, this one can already. Yeah. Then after that, again, same thing. Yeah. So you keep doing this until you can put. Like in this example, I need to put 4 queen. 1, 2, 3. All cannot. Then I have to backtrack. Then this one cannot. This one also cannot. This one also cannot. No more. So I have to backtrack. Then try one more times. Yeah. Then you have to choose the second position. Cannot. Then this one okay. Then this one okay. Then cannot. This one okay. Found. So this is the backtracking algorithm. Of course, same thing can apply to the 8 by 8. Just take some time to let me draw. So I simplified to 4 by 4. Easy for me to draw out the result. Okay, so that is the backtracking algorithm. So for the backtracking algorithm, if it's an 8 by 8 board, actually there are 92 solutions. It's not only one solution. There are 92. I think here I only show you 3 possible solutions. Yeah. If the current column is the first column, and its queen is being moved off the board, then all the possible configure. Yeah. So is after you try the you find one solution at the first position, you can try start from the second one, third one, fourth one, until you try out all the way till the last one. Yeah, you will find out all the possible solution. Every time you find one solution, you just move one more step to find the next one. So total, yeah, you can, in the end, you can find out 92 solution for 8 by 8. I think that is the one of the lab question I want you to do, but not difficult. This is, as I said, this is a very classic computer science problem. Online, you already can find people discuss about it. One of the interesting is this thing. How about 9 by 9? Yeah. How about 10 by 10? Yeah. Why this problem a lot of people discussing? Because actually no one know how many solution in the higher end. They cannot derive the so-called the complexity of this problem. When you have n by n, when you have n by n checkbox, yeah, how many solution can you find? You find that people know that the number of solution is exponentially increased, but they have no idea how exactly the formula, how to find out, yeah, the number of solution is still unknown. Why this one got 92 solution? Yeah, how they derive it out? Yeah, no one know at this moment. Yeah, so that is some problem people discuss. Yeah, about this Adqueen problem. But generally, use the backtracking algorithm, you can let you find a solution. But not all solution. Yeah, you have to try all of them one by one. Yeah, you keep reconfigure your initial position, and then you can find another solution. So that is a backtracking. So summarize, this is the backtracking algorithm. So you will start from I equal to 1 to n. Then you check whether this position is safe to place. Then you place a queen. Yeah. Then you're trying to recursively call the n queen problem for the next column, and then keep doing this. When you cannot find the solution, you will delete the queen and then try another new place. Yeah, so that will be something like this. Actually, as I showed you just now, yeah, then you will try this position, safe to put. Then you will put this one. Then you find that after this you cannot. This one cannot, this one cannot, this one cannot, this one cannot. So you have to backtracking. So after they track the next one, they run through n iteration. They find that cannot, they will return false. When they return false to this one, that means they were trying to delete the queen. So they were trying to delete the queen. Yeah, just like this, they will delete the queen, and then they will try the another position, the following position here or here. They find that also cannot. Then they will return false again, and then delete another queen. Then this one also same thing. After you delete it, no more. Then you will find that you have to go back the first one and delete again. Yeah, you delete again. Then you find the next position. Yeah, then you carry on the recursive. Yeah, then you found it. Then you return true. After successful, return true. You got the answer. Would the complexity of this not possible? Is each row you only find n ma? Yeah. The worst case, n square. Yeah, I think n square is a n by n. You're talking n square, is it? Not n power to n, it's n square. Yeah, because every row only visit, yeah, this position I visit 1, 1, 1, 1. Then this one I visit n. I visit this one. Worst case, I visit this thing n times. Then each position I will visit this one. Worst case, yeah, I think so. Yeah. Let me see. Worst case scenario. That's why you can see that now this one you want to consider what is the complexity, maybe not something easy. You will visit this one, you visit this one, you visit this one, you visit this one. In the worst case scenario, you visit n times. Less than that. Because definitely before that you already found the answer. Then this one also start from here. Yeah, it's another n times. You visit this one also n times. You visit this one also n times. Yeah, probably is n by n. In the worst case, yeah. I only can set. That's why I only put the now I use a big O because not always the case. Yeah, sometimes you lucky you first round already got the answer. Yeah, right. Okay, so that is the quite well known computer science problem, Adqueen problem. Okay, so Wednesday I will cover this dynamic programming. Yeah, I think I already upload this slide to you. You can download the slide in the NTU Learn. Yeah, I don't think I have enough time for me to type another notes for you for this part. Yeah, but actually most of the thing actually here and there actually you are using it. I just trying to Wednesday I just give you an overview what is the dynamic programming. So next time you see the similar algorithm, you know that actually that algorithm is one of the dynamic programming algorithm. You know, okay. Any question? Okay, if not, I think that's all today. For the depth first search directed graph that we went through, if the start is H, we are use the descending order. Earlier, earlier not this slide already. Discuss. Earlier is this one. Your friend said it start from H. If I start from H, okay, let us start from H. If I start from H, ignore the thing, ignore this one, I haven't visit A. So when I visit H, what you want, descending order, you're trying to set in the reverse alphabetical order. I put the H into the stack. Then I'm trying to visit A, B, C, D, E. I visit E first. You're trying to set, I visit E first. Then I will push the E into the stack. Then after that, I will visit C Then I push the C into the stack. Okay, C cannot already. No more already. Then port it out. Then I'm trying to visit D. Then I push the D into it. Visited already. Then next one will be C already visited. Then I only left A not visited. Then I will visit A. Then A still got one more neighbor, two neighbor. Then B and F. I will visit in the reverse way. So I will visit the F first. Then I will visit last one. Then this one F no more. Then I will visit A. Then A still got one more. B. Then B also visited. So this one will be this way. Then just now is visit this one. Then visit this one. Then visit this one. So after that no more already. B port, no more, no surprising. All the nodes already visited. So you start from H. So the spanning tree you expect should be look like this. You visit E. Then you visit E. After that you visit C. After that you visit D. I visit A. Under A, I visit F and B. That's it. So A, B, C port out H, E, D, A, F, H, D, A, F, F port out. Yeah, I think so. Can you upload the answer for last week lab? Okay, yeah. Lab. Okay. I will do that lab upload. But the tutorial I need to wait for a few more days because I think some tutorial group, yeah, they will conduct in this week. Because their tutor do some arrangement. There's no tutorial last week, so they do some makeup in this week. So I need to wait for them to finish it first. Is it safe to say that if the origin is H, then this graph? No. Strongly connected is any vertex to any vertex. You need to make sure that you start from any vertex. Yeah, you always can visit every vertex. So that means if today you are unlucky, you start from H, you find that they are all visited. Yeah, that means the story is not end yet. You have to carry on to search E. How about E? Can or not? D? Can or not? C? Is it same scenario? Is it F? Is it same scenario? Then after you try out every single one, then you can confirm that whether they are this graph is strongly connected or not. You cannot just use one example and then make. But the other way around, once you find one case like A cannot, then you can stop already. You don't need to carry on. Yeah, as long as I can find one counter example showing that they are not connected, you won't be able to find a path from A to H. I can stop already. This is not a strongly connected. Okay. If no further question, I will stop streaming. Does it have a path where every vertex is visited? Does it has a path, or just as long as there's a path to every vertex? Huh? These two statements, is it the same? Does it have to be a path where every vertex is, or just as long as there is a path to every vertex? As long as I can visit, I start from A, then I am able to, through the depth first search, to find out all the path, or breadth first search to find out to visit every vertex in a directed graph. Yeah, that means I definitely there's a path from A to any vertex, right? From A to any vertex. But yeah, as long as there's a path, I don't know. Your first question and second question seems you're talking the same thing, is it? Does it have to be a path? Does it have to be a path where every vertex is visited? Yeah, as long as I can visit through the depth first search or breadth first search, I can visit every vertex from A. That means there's a path from A to any vertex. Right. Yeah. Like earlier example, all this, in this particular example, you find that in the end, H and E, no matter how you start from A, you won't be able to find a path one, because these two are separate one. Yeah, they are you can't find any path from here to H. Yeah, so you try A, try D, try B and C and F. These 5 nodes, you start from this, any one of them, start from one of them, you'll find that you won't be able, you cannot find a way to visit H and E. Whether you use breadth first search or depth first search, result will be the same, because there's no path. There's no path from A to H. There's a path from H to A, but there's no path from A to H. Okay? I think no more question. Okay, thank you. Bye.